Welcome, everybody, to this episode of the History of Science Seminar Series 2024. This is the second in a series of 4 talks, and it's a great honor and pleasure to introduce David Kaiser to you today, our speaker. I've just realized we've known each other for over 30 years. Blimey. David is a brilliant scholar, unlike me. He's also a good cop, unlike me. Whenever we do joint shows, like in the fall, I'm the bad cop and he's the good cop. He's the Gamishausen Professor of the History of Science at MIT, program in Science, Technology, and Society. He's also a professor of physics in MIT's Department of Physics. He has served, and he has told me he's going to serve for the next 30 years. As inaugural associate dean, this is on tape, MIT people take note, for the MIT's cross-campus initiative on social and ethical responsibilities of computing, which he'll be really busy now for the next 30 years. You're welcome, David. David has PhDs in physics and in the history of science, both from Harvard University. Such technical training is as rare as proverbial rubies these days. And for those of you who know about my lament in the history of science, you know second verse the same as the first. His historical research focuses on the development of physics in the United States during the Cold War, looking at how the discipline has evolved in the intersection of politics, culture, and the changing shape of higher education. His physics research focuses on early universe cosmology, working at the interface of particle physics and gravitation. He has also helped to design and conduct novel experiments to test the foundations of quantum theory. He's authored a number of award-winning books, including Drawing Theories Apart, The Dispersion of Feynman Diagrams in Post-War Physics, which looks at how Feynman's idiosyncratic approach to quantum mechanics entered into the mainstream. His book, How the Hippies Saved Physics, charts the early history of the Bell's theorem and quantum entanglement. It was named Book of the Year by Physics World magazine. His latest book, Quantum Legacies, Dispatches from an Uncertain World, was named a Choice Outstanding Academic Title and honored as among the best books of the year by both Physics Today and Physics World magazines. He's edited numerous volumes, including Pedagogy and Practice of Science, Becoming MIT, Moments of Decision, Science in the American Century with Sally Gregory Kolstedt, Groovy Science, Knowledge, Innovation, and American Counterculture with Patrick McRae. And one of near and dear to our hearts here, Well, Doc, You're in Freeman Dyson's Journey Through the Universe. And finally, Theoretical Physics in Your Face, Selected Correspondence of Sidney Coleman, co-edited with Aaron Wright and Diana Coleman. And his work has been featured in many venues, including the New York Times, the New Yorker Magazine, Nature Science, and Scientific American. Please welcome me in joining, please join me, I'll get this ends out in English. Please join me in welcoming David back to the IIS for this talk.
I want to thank Miles and take this opportunity to say that he's going to serve as executive officer of the School of Historical Studies for 9,000 years. So now we're even, Miles, but thank you so much. Sure, I have the lav on too. Hopefully that'll help too. Anyway, well, it's a great pleasure to be here. I'm sorry my throat is a bit scratchy. I take that to be a sign of a really wonderful visit. I've been talking with so many just exciting and stimulating colleagues that I've talked myself hoarse. For someone who enjoys the sound of my own voice as much as I do, this is a real challenge, but hopefully you'll be able to hear me okay in the back. So I'm really delighted to share with you some work from a book project I'm working on a political history of gravity. That's how I've been thinking about the project. How have we come to learn about this very wonderful, very beautiful, esoteric notion of the warping of space-time, as described by Albert Einstein's crowning scientific achievement, the general theory of relativity? And how has that come to affect how many of us lead our lives in ways we might not have expected from the start? There's a rather late chapter from that history. I'll be looking at some recent history in the 1970s and 1980s. But I'll start by turning the clock back quite a bit earlier. I don't have to say too much, I don't think, about GPS, the global positioning system. I think many of us, and perhaps all of us in the room right now, make use of this most days. I certainly use it all the time. I have a terrible sense of direction. It's become a ubiquitous consumer technology. We use it when we're navigating in our cars. It's a mainstay, for example, in civil air transportation and so on. There's some, sorry, I'm getting a little feedback if the folks can. Oh, thank you. Okay, that sounds better. Thank you. There's some wonderful scholarship I'm building on from some colleagues. Bill Rankin, who's another really just marvelous historian of science and technology, has a fascinating book you might enjoy called After the Map. Some other books that I've really benefited from as well. GPS has been around long enough, we can literally give a cartoon version. This is thanks to the Smithsonian. In a nutshell, what GPS is doing when we use it for our handheld receiver devices is we're receiving signals from usually at least 4 satellites overhead. The signals are complicated in structure, but they boil down to 2 essential pieces of information. Number 1, they're beaming down where they are, their own location. And the second piece of information they beam down is what time their onboard clock says. I'm here now, is essentially what they're announcing kind of continuously. And then those are relayed by radio signals down to the ground, so that on many, many parts of the surface of the Earth these days, at most times of the day, there will be at least 4 of these satellites overhead, and our devices can collect those signals from at least 4 of these orbiting satellites out of a network of at least 30. So our receivers here are using a very complicated equation. The distance equals speed times time. That's the most important one to remember. There is no quiz, but that's the most important one to remember. Why does that help us? These signals say it's this time now on board the satellite. Our local receivers have their own clocks. So by comparing the time when the time stamp of that signal, the time at which the signal is received, the receiver can very quickly calculate the time that it took for that signal to travel. These are radio waves. They're traveling essentially at the speed of light. So the speed at which they're traveling is well known. And that means that the receiver here can calculate the distance from that satellite to here. And if you do that with 4 of these, you can solve 4 equations for 4 unknowns. We want to know where we are in space, east, west, north, south, up, down, that's 3. And also when we are in space-time, what's the time? So we need 4 signals we want to solve for 4 unknowns. Where are we, and so to speak, when are we? And so our receivers are doing that at lightning speed all the time, really by making use of the fact that these satellites are sending time-stamped location information at the speed of light. And so that's obviously an oversimplification, but that's the gist of what's happening with this network of satellites that helps me navigate from Via Lane here to Wolfensohn Hall and so on. So for many of you in the room, maybe in this room, all of you in the room actually, once you start asking about clocks on satellites moving fast, zipping around, you're going to start wondering about things like relativity. Many, many of you will be asking those questions right away. Einstein's theory of relativity predicts that both motion and indeed gravitation should affect the measured rate at which clocks will tick. We won't all agree on the rate at which a clock is ticking if we're moving very fast with respect to one another, or if I'm sitting in deep empty space and you're right near a very large mass. Here's a nice quotation from colleagues Cliff Will and Nico Yunez. They wrote a lovely book called Is Einstein Still Right? The spoiler alert seems to be yes, he really still is. And they write, without the proper application of relativity, GPS would fail in its navigational functions within about 2 minutes. That is to say, the errors would propagate and grow to be about 7 miles off per day. I'd never find my way from Via Lane to here if we didn't correct for these relativistic corrections. So Cliff and Nico say the next time your airplane approaches an airport in bad weather, and you just happen to be wondering what good is Einstein's theory in this room, that's a realistic quandary, think about GPS in your cockpit helping the pilots guide you to a safe landing. Okay? We really rely on this in ways we sometimes don't even recognize all the time. The physics underlying these relativistic corrections for different clock rates is so well understood, it's now put into some very lovely undergraduate textbooks on gravitation. Here's one of my favorites by Jim Hartle, simply called Gravity, an Introduction to Einstein's General Relativity. He has a lovely several-page spread on the physics of GPS relativistic corrections. There's some very doable but substantial homework problems we can now assign to gifted undergraduates. We think we know this very, very well. And yet it took a long time to get there, and that's what I want to dig in with you tonight. So long before GPS became a widespread consumer technology that many of us have in our pocket, it was actually a secret military technology. And for about a decade, between the mid-1970s into the mid-1980s, a debate simmered largely behind the scenes among theoretical physicists, electrical engineers, military strategists, over how to incorporate relativity within GPS. Not whether to include relativity, but who's getting it right. The stakes, by the way, seemed enormous, as so many things did during the late Cold War. several people raised alarms about immediate nuclear annihilation. So suddenly it's worse than me getting lost from Violaine. It's suddenly triggering nuclear war. And this was wrapped up with very bitter, protracted concerns about secrecy, about special interests, about profit motives, about expertise. Who's going to get this right because the stakes seem so important? So I'm going to walk us through three parts tonight. To get to these dueling relativists, we have to first step back and think a little bit, remind ourselves for those for whom it's familiar, and hopefully give at least a brief introduction for those to whom it's new. Why would anyone think relativity has anything to do with the rate at which clocks are measured and so on? That's going to be a little reminder here in part one. Next, I want to turn back the clock not quite as far back. And that's, where did GPS come from? Long before it was so ubiquitous, it was, as I say, a largely classified military technology in the US. And then we'll see how these very smart folks had to deal with these subtle corrections. So Albert Einstein emerged with his really crowning scientific achievement, the general theory of relativity, in the month of November 1915. In fact, we know almost day by day his progress. This is one of the best documented episodes in the history of science to court. Right? This was covered by his personal notebooks. Here's an example of his personal notebooks, the so-called Zurich notebooks from 1912, 1913. I love these because he's making all kinds of often quite trivial mathematical errors. I feel better. I make errors. I'm no Einstein, but I make the same errors. So we have that in common. We have this amazing gift to our community, edited by friends of ours, called The Collected Papers of Albert Einstein, with thousands and thousands and thousands of pages of previously unpublished private correspondence, incoming and outgoing, as well as reprints and translations of his papers. We have a very, by now, extensive and very good secondary literature by scholars who've pored over these primary sources for a long, long time. So I won't recreate his 10 years of false starts and crossouts and conceptual confusion. I'll cut to the chase. At the end of that decade-long journey, not at the beginning, he arrived at what we call the field equations that are going to be familiar to many of you in the room, that we still use every day. We call these the Einstein field equations, or the governing equations of general relativity. They look remarkably simple. I often tell my students, if they're in the market for body art, you could do a lot worse. This is pretty good tattoo material. This side here is the mathematics quantifying the degree to which space and time are warping, are deformed. These are basically gradients, first and second derivatives, the rates of change of things like the spatial metric, how we lay out coordinates in our vicinity, how our clocks might change over time. And those are set equal to where the stuff is, to the distribution of matter and energy. And so another great Princeton mind, John Wheeler, famously said that these equations can be read in either of two ways. You can say that space-time tells matter how to move, or you could say that matter tells space and time how to curve. It's this beautiful bringing together, unification of the geometry, the warping, the distension of space and time, and where the stuff is that's committing that bending. So again, Einstein didn't start with this conception. By the end of this really quite extensive 10-year journey, he's convinced himself, though few others at the time, that gravitation has nothing to do with forces, with the sun exerting some tug on the Earth. It's not about a Newtonian system of forces. It's really just nothing but geometry. It's about a large mass like the sun affecting its own surroundings, the space-time around it, and the much smaller objects like the Earth moving in as straight a path as it can through a region that's no longer flat. There's curvature here because of the large mass of the sun. That affects the motion of the Earth, and so on. So the Earth falls in its orbit not because of some mutual attraction like Newton would have said, but because the sun has literally warped its own surroundings. There's a lovely, lovely literature now by many friends and colleagues studying various aspects of this. How did Einstein get there? How did other people make sense of these very strange sounding ideas? What were some of the earliest efforts to test some of these ideas empirically, quantitatively, which were very subtle and very complicated? Some really lovely books here that I strongly recommend. I also want to remind us that cartoons like this, I think, are very helpful, but they're still limited. This emphasizes the warping of space. We see this as if it were the surface of a trampoline that's been bent. But especially important for our story tonight, the equations also say there's an effect on clocks, on the measured rate at which time will pass as well. The clocks are being warped as much as, say, this sort of spatial fabric of a trampoline. So I like this painting by Salvador Dali to remind us this is about the warping of clocks as in their readouts, as well as the vicinity, say, of the sun. So I want to walk through three distinct ways that Einstein and a small circle of colleagues in the early years of the 20th century argued that relativity should affect the measured rates at which clocks will tick. The first predates general relativity, goes all the way back to his groundbreaking paper in 1905 that introduces what would come to be called special relativity, his paper on the electrodynamics of moving bodies. Einstein, at the tender age of 26, convinced himself that light was very special, that light should set a kind of universal speed limit. He convinced himself, though at first very few others, that nothing could travel faster than light. And even more important to Einstein, he convinced himself that people in motion with respect to each other would nonetheless agree on the rate at which light was traveling. So then he realized you could use light as a really terrific measure of the passage of time. You could create what became known as a light clock. And he actually wrote about this in this very famous paper. Imagine you have two very highly polished mirrors. You hold them a fixed distance apart, some height h. And you mark the passage of time by passing a light beam from the bottom mirror to the top mirror. Now, if light travels at a fixed constant speed on which we'll all agree, that's a terrific standard, a terrific universal standard for measuring the passage of time. If you hold the height fixed, then the light beam can't speed up or slow down. It can only but travel at a fixed speed, and that use that to mark your delta t, your passage of, say, 1 unit of time. What if your friend has an identical light clock, same mirrors, same manufacturer, but she's racing past you on a very high-speed train? Einstein loved trains. So you have a train that's moving impossibly fast, some large fraction of the speed of light. And you watch your friend zip past you. You stand on the train embankment, and you watch her zip past while she holds her mirrors the same height apart. And you watch the progress of her light beams in her light clock. So you're going to watch them trace through this zigzag pattern, because as soon as the light beam leaves the bottom mirror, the entire assembly starts moving. And so in order to hit the top mirror, the light beam has to travel on this hypotenuse of that right triangle. And according to Einstein, at least he convinced himself, the light beam couldn't speed up to make up the difference. So we're going to see our friend's clock tick more slowly than our own, because the light beam has a further distance to travel as far as we're watching it move, and it can't change its speed. So Einstein concludes as early as 1905 that relative motion at some high speed will mean that I measure the moving clock to tick more slowly. And the trick is, our friend on the train measures our clock to be moving equally slowly. It's perfectly symmetrical in this case. So this became known as time dilation. This comes from rapid relative motion. Okay, that's step one, introduced already in 1905, and that carries over, it turns out, into his more mature work 10 years later. On the road between 1905 and 1915, Einstein begins wondering about things like accelerations. He eventually begins thinking about gravitation. And he comes to this second idea a few times over. He publishes a number of articles. The quantitative calculation shifts, but the basic cartoon picture in his head held pretty steady. And that's a question: what would happen to a light beam that's now traveling in some region of large space-time curvatures, something like leaving the area of near the sun, or in an even more dramatic mass? What will the effect be on that light beam as it expends energy to climb away from this region of stronger space-time curvature, stronger gravity, toward a region of lesser curvature, weaker gravity? So again, he realized light beams are special, at least to him. We can use the frequency of light as a clock, the time it takes between the arrival of distinct crests of this light beam. So again, over the course of the 1910s, he comes back to this over and over again. He's fiddling with his coefficients, but the basic idea stays pretty steady, that a light beam that has to climb out of this, we'd now say a gravitational well, has to expend energy. That means its frequency will shift. It will literally change color. What that means is that the time between the arrival of these crests will get stretched out. So now it's not about relative motion between the emitter or the receiver. It's the idea of being near even a static large source of gravity, a large significant curvature of space-time, will have the effect of slowing down a clock. Strong gravity slows clocks. This becomes known as gravitational redshift. And this is again incorporated into his kind of final version of the theory a few years later. There's a third distinct source by which will make people in relative states of motion disagree on the measured rate at which clocks will tick. And that has to do with rotations. This was actually first really diagnosed by a different researcher, Sagnac, in Paris in the early 19-teens. Sagnac thought this was the death knell of relativity. He thought he would disprove Einstein. And instead, within a few years, one of Einstein's colleagues was Paul Langevin, also in Paris, realized this is actually a feature, not a bug. There's actually a distinct prediction from relativity that observers who are in mutual rotation will also disagree on the rate at which clocks will tick. So the idea goes like this. Imagine we have an array of observers with identical clocks, and let's say they're positioned around the equator of the Earth. So they're rotating as the Earth rotates from day to night. They're moving with the Earth. Let's say they want to set up a relay and use light beams, because light beams are special, to synchronize their clocks. So the first person here says, my clock struck 12 noon, sends that as a light beam over here. This person here knows how far distant they are, so she knows to offset her clock. Once she receives the 12 noon signal here, she knows it must be 12 noon plus the travel time. Then she relays it like a relay race, passing the baton all the way around. So they know how long, all these observers will agree how long it should take in time to complete that relay race, trading that light beam all the way from the starting clock all the way around to get back to the start again. And the time it should take would be the distance to travel, in that case the circumference of the Earth, divided by the speed at which the light beams travel, the speed of light c. What if there's a separate observer sitting at the North Pole who's not rotating? And she's watching this whole thing unfold. She's going to disagree on how much time it takes to complete a lap. Because as far as she's concerned, as soon as the first clock emits the light beam, it starts moving. So it's like it's a moving target. So to complete a lap, by the time the light beam comes back, this observer has already rotated some distance. So the non-rotating observer at the North Pole says it's going to take a different amount of time, in this case a longer amount of time as far as she's concerned, to complete that lap by trading the light signal to synchronize your clocks. This became known as the Sagnac effect. And again, it was a calculable offset clarified by the French physicist Paul Langevin in the early 1920s. So over the opening decades of the 20th century, Einstein himself and a modest small circle of colleagues had identified three quite distinct ways or reasons why relativity would affect the measured rates at which clocks will tick, the measured rate for the passage of time. This time dilation comes from relative motion at high speeds. Gravitational redshift comes from being near or not so near a region of strong gravitation, strong space-time curvature. And the Sagnac effect comes from these rotations. Do you see this baton relay race from one rotating frame or not? Now, these effects were very tiny. These were not things that would show up on a typical clock if you're walking around Switzerland or Berlin. In fact, they eluded clear measurement for decades. So these were hypothetical. They were clarified conceptually by the early 1920s. The small circle of relativity experts agreed these are predictions of the theory. They were by no means sort of solid experimentally verified, but they seemed like unavoidable consequences of the theory of relativity by the early 1920s. And again, some really wonderful literature by friends and colleagues on many aspects of that. Let me shift gears. I'm going to move the clock forward now into starting now the mid to late 1950s. So we have relativity on hand. What about this GPS thing? And here's a quick reminder, GPS really was starting life as a classified military technology. There's a photograph that I love. It shows you can see from the uniforms, US Army, who had access to GPS. This is what the receiver looked like. This would not fit easily in your pocket. This is what was called, with no sense of irony, a GPS man pack in 1978. No further comment needed. So where does this come from? There's a parallel stream, seeming to have little to do with Albert Einstein. This dates to the earliest days of the space age. The ideas for GPS started literally on the night that the Soviets launched the Sputnik satellite on October 4th, 1957. Two researchers at the Johns Hopkins Applied Physics Lab were intrigued, as many, many people across the world, certainly across the United States, were intrigued by the Soviet launch. These folks who worked at APL, the Applied Physics Lab, they were experts on various defense-related technologies. Their day job was developing technologies, for example, to track guided missiles. Some of you may know the Hopkins Applied Physics Lab was launched early in the Second World War to work on various classified defense projects like the proximity fuse. And it stayed on as a very active Cold War laboratory. It's active to this day, but certainly active in this period for, again, kind of radar-based tracking of things moving fast, like guided missiles. So it was actually not so hard for those folks to start tracking the Sputnik satellite. with their existing technology. Here, it was these gentlemen here, William Geyer and George Weifenbach. Here they're shown with their supervisor at the lab a few months later, Frank McClure. So they realized after successfully tracking Sputnik, they could reverse that procedure. They imagined, what if we put our own sort of speaker, our own transmitter on our own purpose-built satellite, and we used the receipt of signals from a satellite at a known location to tell us where we are on the Earth. Instead of saying we're here on Earth watching the satellite, what if we reversed that? And so this part, I've been a Cold War historian of the Cold War since I've known Miles for a few years. And I still get struck by the rapidity of this. So Sputnik's launched in October '57. That spring, they put together an entire proposal to the US Navy to reverse that technique. It's fully funded and operational within about a year and a half. It's lightning, unbelievable. This is one of the earliest funded projects by the then new program called DARPA, which I'm sure is familiar to many of you, the Defense Advanced Research Projects Agency, or DARPA. This became known as the Navy Transit System, and it really actually worked. Of course, the US had famously some difficulty getting the first satellites launched, but by 1958-59, the US also had several satellites in orbit, some of which were purpose-built for this Navy system, engineered by the Hopkins lab, where they had transmitters on these orbiting satellites to beam down, basically, like I said in the beginning, sort of, I'm here and this is the time on my clock. And they were used for naval navigation, operational already by the end of 1959. In parallel with those developments, there was a lot of really enormous improvement in the study of clocks themselves, the design of clocks themselves. There were these so-called atomic clocks, or really atomic frequency standards, have been another kind of byproduct, unexpected byproduct of the wartime research on microelectronics at places like MIT with the RAD lab and Hopkins Applied Physics Lab and UK and many parts of the world. By understanding and developing methods to measure to exquisite accuracy the timing of certain very subtle atomic transitions, for example, in a cesium atom or rubidium atoms, or some of these particular atoms, people were able to design clocks that were stable to parts per trillion. They would lose on the order of 100 nanoseconds over the course of an entire day. That was just orders of magnitude more precise than the existing timepieces before then. These were designed and constructed in a series of government laboratories in the US and the UK, especially other parts of the world, but the US and UK happened to be quicker on this technology. And then they became more widely available in the 1950s. These were under development very soon after the end of the Second World War, with the sort of surplus microelectronics and expertise from the wartime projects. And roughly 10 years later, there were kind of working versions that were no longer only tied up in government labs. 10 years after that, in the mid-1960s, this gentleman, Roger Easton, who was working at the Naval Research Laboratory, said, let's use these really good clocks on satellites to do navigation. Let's do that Navy transit system, but with really, really accurate clocks. If your clocks are that much more accurate, you should have that much more accurate positional information on the ground. So he wanted to have these send time-stamped signals from these exquisitely precise clocks instead of the other ones. Then you could actually synchronize clocks across large distances with confidence that your clocks are ticking at a comparable rate. Unbeknownst to Easton at the time, in parallel, the US Air Force, not the Navy, now the Air Force, was working with a private defense contractor called the Aerospace Corporation based in Southern California. They had a very similar idea. This was classified at the time called Project 621B. I don't know if there was a 621A. I don't know if there was a 622. I don't know. But their idea was to put atomic clocks, atomic frequency standards, on purpose-built satellites to beam down time-stamped information. In this case, not for navigation per se, but for targeting. I want this weapon to be dropped exactly where I want it to go, similar kind of goal. I want exquisite ground-based positional accuracy for either where things going to fall or where I am. There's some really path-breaking work by our colleague Paul Foreman, I want to just call out here, who studied many of these kinds of kind of spillovers, let's say, of World War II era microelectronics into a whole range of sometimes consumer, but often still quite focused on military type applications during the years after the end of the war. These are examples of this kind of swords into plowshares that Paul had written about many years ago. So almost 10 years after that, the Pentagon said, we have these kind of agencies pursuing different and kind of competing projects. Let's bring them under one roof. So beginning in 1973, just over 50 years ago, the Pentagon formed the first GPS Joint Program Office based at the Air Force Base in Los Angeles to coordinate these efforts across what had been really kind of rival service branches. Here's a clearly staged photograph. This is Air Force Colonel Brad Parkinson in his dress whites. He was in charge of this new Joint Program Office, working with a colleague from the Navy and a colleague from that defense contractor, the Aerospace Corporation, symbolizing now they're going to work very closely together. And the main goal, as you can see, was guidance systems for weapons delivery, precision targeting of munitions. So within a few years of when the office was set up, they were able to launch their first purpose-built GPS satellite, a new generation. It was launched from Vandenberg Air Force Base in California in June 1977. And within half a year, they were already doing target test runs at the Army Proving Grounds in Arizona. I love this photograph. This is the Arizona Senator Barry Goldwater inspecting one of the test runs. He's listening in on a manpack. I don't know what he thought he would hear, but you see this is such unusual technology. He wanted to get really up close to it. And this was indeed a successful test run where they wanted to see, could they drop 5 bombs in a row in the same hole? And this was the first time where they were able to do that with the help of this targeting from these satellites. So Parkinson, the Air Force colonel, put up these sort of motivational posters around the program office, and you can see he wanted to keep his colleagues focused. The idea is to drop 5 bombs in the same hole, build a cheap set that navigates, and don't you forget it. That's how you motivate your colleagues. 10 years after that, this was already operational as a fully operational system, not just testing at Yuma. And it was actually being used to target nuclear-tipped U.S. cruise missiles for SAC, Strategic Air Command. So within 10 years of the first test runs, this was deemed operational enough for things like guiding U.S. nukes. Okay, let me come to the last part, the part that, frankly, I find most curious and really most interesting. These dueling relativists. So again, as many of you in this room will know, the speed of light is very fast, at least in human terms, roughly 300,000 kilometers per second. That means light travels about this far, roughly 30 centimeters, in a billionth of a second. It's really fast. So if you want to have location accuracy for targeting or for navigation of about 1 meter, if that's your kind of error budget, that means you have to trust your network of coordinated clocks to within 3 billionths of a second. Because that's how far light's going to travel in that long. You're going to be off by 1 meter if your timing is not sufficiently precise with an error budget of 3 nanoseconds, 3 billionths of a second. So by the mid-1960s, as atomic clocks, atomic frequency standards, are becoming more accessible, not just only at special laboratories, many researchers in astrophysics, in physics at the contractor sites, began to study whether and how to incorporate relativistic corrections within for something like GPS, if your clocks that are moving end in differential gravitational fields. Much of this work was published in the open peer-reviewed literature. Here's an article by a Japanese researcher in the Astronomical Journal. Here's an article in the very prestigious Physical Review Letters by a researcher at that Aerospace Corporation. If your error budget is 3 nanoseconds, then you have to worry about otherwise very subtle effects like time dilation, redshift, and perhaps rotations. That was in the open literature as a question, as something we better pay attention to this as early as the mid-1960s. Let me remind you about those first 2 relativistic effects that had been identified long before there was a Sputnik satellite or GPS satellites. The first is time dilation, a disagreement on the rate at which clocks will tick based on a very quick relative motion between 2 observers. And the second being gravitational redshift, the difference in clock rates based on whether you're in a strong gravitational field or a weak gravitational field. Let's take the first one, time dilation. To an observer on the ground, these GPS satellites move really fast, on the order of 400 kilometers per second. Not the speed of light, but fast compared to cars on the turnpike. So these GPS clocks on the satellites would run measurably slowly compared to the reference clocks on the ground. We see the satellites zip past us. We see them moving really fast. We therefore measure their clocks to tick at a more slow rate than our otherwise identical clocks on the ground. On the other hand, the satellites are really high up. They're on the order of 20,000 kilometers above the Earth's surface. They're feeling a much weaker gravitational field than we are on the surface of Earth. So the gravitational redshift goes the other direction. The gravitational redshift affects the satellite clocks less strongly than our Earthbound clocks. They don't exactly cancel. And so you have to actually do a pretty careful calculation for the actual orbital parameters of those GPS satellites. and say which will win. In a sense, they're in opposite directions, but not equal and opposite. And so for those characteristics of those satellite orbits, it became clear that there would be a measurable offset of a few hundred parts per trillion, which doesn't sound like much, except if you have atomic clocks that are accurate by this point to better than parts per trillion, that's going to be in your error budget. In fact, it's going to exceed your error budget. And so it became clear that if you ignored that difference in clock rates, the rate between the clocks on those satellites and the clocks here, in your pocket or in your man pack, then accuracy, you'll lose the 1 meter accuracy within minutes. That suddenly hundreds of parts per trillion in time translates into a big enough divergence in space that you're no longer going to have meter scale accuracy if you want to do things like drop 5 bombs in the same hole. Now that was clear enough to the experts who actually knew relativity. It was by no means persuasive to the otherwise extremely hardworking, gifted engineers in the DoD projects who were actually building these things, launching satellites, calibrating the atomic frequency standards. Many of them were skeptical about any of this strange-sounding relativity stuff, not surprisingly. So many of them said, you basically keep your relativity off my fancy clocks. Like, I got this, right? Keep your equations away. Other engineers were so convinced by these arguments, they actually double counted the relativistic corrections. It's subtle. And I say that not to tease the engineers, saying it's not so straightforward. Some of them counted gravitational redshift and then counted it sort of a second time, thinking it came back in a second way. So there was great confusion about whether to include these corrections at all, and if so, frankly, how to include them. And some of the physicists who consulted on these projects wrote about this nearly in real time, within only a few years. So we have an almost contemporaneous account of some of these early kind of hiccups in incorporating relativity into GPS. The skeptics were quieted down pretty quickly with actually that first launch of the first purpose-built GPS satellite launched, as I said, in June 1977. It carried on board a relativity switch. I love this. It shows you the practical engineers who would trust the physicists, but only so far, which shows you they were actually pretty smart. So the engineers on the ground said, you can't mess up our clocks, but we'll allow you to put in a software code. So if we're going to launch the satellite with our pristine clock that you physicists haven't been able to touch. And we'll let you then send a signal from ground to satellite to then trigger a software switch. The software, when triggered, will start reporting out the onboard clock at the wrong rate, at a rate that takes into account these hypothetical relativistic corrections. They didn't change the clock, they changed the way the clock's output would be reported in those signals that are beamed down by radio waves. And they wouldn't do that until the thing was already safely in the air, in the sky. So they actually performed this measurement with that very first test satellite. Here is the measured offset between the ground and orbiting satellite, and the offset grew at precisely the rate predicted by general relativity. It's an early precision test of GR to better than about 0.5% level accuracy. So the offset between ground and moving satellite actually matched the predictions beautifully well. Then the engineer said, okay, now you can throw your switch and send the signal up to the satellite to change the rate at which the clock is reported out. Don't touch the clock, just change the software. And then the rates became parallel again. That quieted the engineering skeptics. This was reported in the open literature in a conference proceedings at a conference held actually not too far from here in New Jersey at one of the, I forgot which of the Army Research Labs, published in the open proceedings, but not in a kind of peer-reviewed journal, kind of hard to find at the time, but nonetheless not classified. It was published within 1978. After that, the engineers did what was called factory offset. So instead of having to kind of manually throw a switch to throw a command to change the software, the clocks before the satellites were launched had this software routine put in on the onboard computers. So the clocks would tick at their rate, and the computer would automatically adjust the rate at which that was reported out without having to send that signal. Even that was not so straightforward. Here's a letter I found in the archives I found really fascinating. Several years, almost about 8 years later, they had to apologize because the chip didn't work. Send us your chip back. We'll show you how to replace it. It still wasn't quite so straightforward to do this factory offset, even once they all agreed they had to do that. So that covers time dilation, fast relative speed, and gravitational redshift, different gravitational potentials. What about that third effect, that so-called Sagnac effect, the effect of rotations? Here was what was for many, many years the most prestigious textbook on the general theory of relativity available in English, It was an English translation of a Soviet textbook, a marvelous Soviet textbook by Landau and Lifshitz called Classical Theory of Fields. This was published in translation in 1955, and it really wasn't bested, I would argue, until really the early 1970s. Landau and Lifshitz have a whole section on the effect of rotations on doing things like synchronizing clocks. This is strictly a hypothetical challenge when they were thinking about it in the 1940s when they first wrote the book. And you can see they actually conclude clocks on a rotating body cannot be uniquely synchronized at all points. They say the Sagnac effect is real. That's a real feature, an unavoidable feature of general relativity. So if you have clocks that are in relative rotation, they will not agree on the measured rate at which time will pass either. So just at the time that that first dedicated satellite was being launched, the one I mentioned, NTS-2, and they have this sort of relativity switch and all that, independent of that, in fact, with sort of no clear connection to all that, a quartet of outsider physicists was getting very concerned about the little they could find out about GPS with what they actually knew quite well about general relativity. I'm going to refer to them as sort of the outsider quartet. It was Jeffrey Cohen, Harry Moses, Arnold Rosenblum, and Angelo Scalafouris. They began writing a series of articles, again, in highly prestigious peer-reviewed journals like Phys Rev Letters, like Classical and Quantum Gravity, like an electrical engineering journal, arguing that based on what has been at least published in the open literature, GPS can't possibly work as claimed, because relativity, in particular rotations and the relativistic Sagnac effect, will kill it. They published their extensive calculations in these peer-reviewed journals. They say synchronization errors of 9 microseconds, 3,000 times worse than your error budget, are going to accrue with every orbit because their satellites are rotating with respect to us on the ground. So if you need 3 nanosecond accuracy as your error budget for synchronizing clocks, and you're off by a factor of 3,000 because of the rotations, then instead of having 1 meter accuracy for your navigation or your targeting, you're going to be off by 3 kilometers, which again is not very useful for its intended purpose. And they were very concerned. They were extreme, as I'll show you in the next slide, they were extremely well trained on the relativity side, and they were not quiet. I won't go through all this. I want to say who were these quartet briefly. Jeffrey Cohen was a professor at Penn at the time, PhD from Yale, postdoc right here, so it couldn't have been that bad. His dissertation was called Rotating Masses and Their Effect on Inertial Frames. He'd worked on this problem since he was a graduate student. Okay. Harry Moses was a more senior professor at UMass Lowell, member of the New York Academy of Sciences, and on and on and on. These were PhDs in relativity, in astrophysics from elite programs, award-winning scientists, very concerned about what they read, the little they could have access to about the still largely classified military technology, because they were experts on things like rotating frames in relativity. The next step heightened their concerns. So the theoretical framework for incorporating all these relativistic effects within GPS had largely been worked out by 2 physicists based in Boulder, Colorado, Professor Neil Ashby, who was at the university there, and his colleague David Allen, who was a staff scientist at what was then called the National Bureau of Standards, which is now NIST, the National Institute for Standards and Technology in Boulder. They worked this out, basically worked out what we would now call the kind of coordinate system, the reference frame with respect to which to calculate all these different relativistic effects, specifically for coordinating GPS clocks. They were kind of contractors on the inside, so to speak, for the GPS project. And a lot of their work was also available in unclassified forms, but not very convenient forms. One of the most extensive descriptions of this kind of reference frame system was published as a government report released by the Department of Commerce, because Commerce had control of the National Bureau of Standards. So they're working at Boulder at what is now NIST, and their kind of parent federal agency released a kind of gray body white paper, non-peer reviewed, not in a scientific journal, not stocked in every library. The 2 of them also published a more technical article in an electrical engineering journal, a peer-reviewed engineering journal. And actually, the most user-friendly version was not published at all. It was completed for an Air Force contract for internal use. I found this in Cliff Will's archives. So you have a series of things that are not super accessible, one of which is peer-reviewed, but by experts in electrical engineering, not, say, in general relativity. So that outsider quartet I mentioned, Cohen, Moses, Rosenblum, and Scalafouris, they got very concerned. They got their hands on the electrical engineering journal article. They read it, and they said they've messed up rotations. The whole thing can't work at all. So they did what I think would be every scientist's nightmare. They sent the published article out for post-publication peer review. Can you imagine? It's already out. Give me a break. So on their own, they sent this out to their own selected experts in relativity to say, don't take our word for it. Look at these experts in relativity, and they'll tell us whether to trust this published peer-reviewed version of whether the coordinate systems, the reference frame, is going to be adequate for GPS. So they got these letters back. I won't read them all. These letters went on for pages and pages. This one did. This was just British and brief. This was from Professor Seifert in Hamburg, West Germany. There's 5 typed pages. I'll just read some choice excerpts. So this, remember, so the outsiders sent the published article by the Boulder physicists to these external reviewers, post-publication. Seifert says, unfortunately, this paper, meaning the one by the Boulder physicists, presents neither correct results nor a clear description of the problem. That doesn't start well. It uses pre-relativistic language, which is an incredible insult. In fact, the fundamental equation, literally equation 1 of this published article, on which the rest of the paper is based, obviously does not take the important effects of rotation into consideration. Basically, the results as they stand cannot be used. Okay, that's the end of page 1 of 5. It doesn't get more happy after that. The British researcher, Professor Clark, writes with a very similar conclusion, I find this paper by the Boulder physicists quite unacceptable as a basis for a theory of measurement within general relativity. Because the underlying assumptions were incompatible with relativity itself. It ignores rotation. The metric they use is static, transformed into rotating coordinates. It does not include the effects that would be most relevant. I recommend that no reliance be placed on these authors' results unless they can be obtained by other means. Okay. So then this outsider quartet mails these unsolicited referee reports to the Air Force, not to the Boulder physicists, because they're pretty smart, they say, not only are we sending you these referee reports, we're asking you for money. This became part of an unsolicited grant proposal to the Air Force by Cohen and Scalafuris in December of '83. And you can see here that this is now from their unsolicited grant proposal. Although described as a navigational system, this GPS constellation of satellites will greatly benefit the Defense Department. Let's not tease each other. It's a military technology, they're saying. Present-day use of cruise missiles, ballistic missiles, precision strike systems depend on high accuracy within 1 meter. That's the error budget. And yet to do that, it's necessary to synchronize clocks within 3 nanoseconds. And as shown in their own articles published in the most prestigious physics journals on the planet, like PhysRev Letters, an error that's substantially larger is going to accrue because of relative rotation. Then there's this part I found especially interesting. The mechanism by which these relativistic corrections are carried out does not seem to be available to inquiries, let alone published in either the open or the classified literature, according to telephone conversations with personnel at IBM, Magnavox, and Aerospace Corporation, from whom the synopsis was obtained. They had to start calling the contractor saying, how are you incorporating relativity? And the contractor said, well, we're using this one published article, the one that the outsiders just had trashed by the experts in West Germany and Britain. So unfortunately, that article, they say, would be considered erroneous by the physics profession and can't be used. And there's a cover letter, separate from the proposal itself, but in the cover letter that Scalafuris sent to the Air Force General when he submitted this grant proposal, he says, I'm actually a licensed engineer as well as a theoretical physicist. I understand a practical approach to problem. I'm not trying to be, an ivory tower perfectionist. So we're not saying we're right. We're saying it's ambiguous. Please have this looked at by people with no conflict of interest. So if you're only trusting the contractors whose contracts depend on doing what they're already doing, maybe you're not getting the best advice. And this part he goes on to say, and in the cover letter, we are severely handicapped by the unwarranted secrecy surrounding the relativistic corrections. All we can do is speculate on how someone with intelligence yet without training in GR, and I want to look at how generous that was. There could be such a thing as a smart person who happened not to have been trained in GR, and yet such a person, we have to guess at how they would attempt to solve such a complicated problem. He then begins a barrage. This would be, if this was emails, this would have been a denial of service attack. He's sending letter after letter after letter, day after day after day, week after week, to the same Air Force office. Here's a follow-up letter from a few weeks later, because he hadn't yet gotten a kind of sufficient, to his mind, sufficient response. He says, it's not just because we're disagreeing about the equations, you're about to trigger nuclear war. That starts getting Air Force generals' attention, it turns out. And he has several arguments to that follow-up. Accuracy in targeting for ballistic and intercontinental missiles implies smaller payloads. If you actually can target a weapon to within 1 meter, then you can build a less destructive weapon. if you really can't hit within 1 meter, you're forced to make a larger warhead, and you're going to trigger a new round of escalation, of runaway escalation in the arms race. That's his concern there. That really was a concern at the time. There's a marvelous book, many of you in the room will know, by our colleague Donald Mackenzie called Inventing Accuracy. Inventing because accuracy, by what standards to whose needs? And in the context of ballistic missile targeting, there was this presumed trade-off between accuracy of delivery and the size of the destructiveness. And if you can only hit a target within 3 kilometers, then the argument was you're going to go for megatons in nuclear weapons. And that's not something that these folks wanted to see happen. So number one is if you really can't get the targeting right, then you're going to be forced to trigger a new phase of a runaway arms race. Second, the Soviets are really smart. They're going to call your bluff. They know relativity after it was a Soviet textbook, Landau, Lifshitz, and a whole thriving community of world-class relativity experts in what was then the Soviet Union. So if you're trying to negotiate arms reductions with Soviet experts, and you're claiming that you're going to otherwise threaten them with meter accuracy targeting, they're going to call your bluff. So you can't do it, you make bigger warheads. They know you can't do it, that doesn't help in negotiations. Plus, the NATO allies are relying on us, and we're going to let them down too. If you send enough letters like that, empirically speaking, the Air Force finally stops and pays attention. So within months of this barrage, a brigadier general of the Air Force said, okay, it's time for an outside review after all. And that triggered this blue ribbon committee from the Air Force Study Board, chaired by our colleague Clifford Will. There's a much younger looking Cliff who was asked to chair it. Clifford had done his PhD with Kip Thorne in the sort of a renowned relativity group at Caltech. By this point, Cliff was a young professor on his own at Washington University in St. Louis. He'd only recently published his magnificent monograph. It's still in print in the 2nd or 3rd edition called Theory and Experiment in Gravitational Physics. He was the right person to lead this on. And as you can see, the committee included several other leading academic experts in relativity, some experts from the national labs, some experts from defense contractors who were experts in things like what was called time transfer and other kinds of space technologies and satellites and so on. And here's how they began. Here's what got them to their first meeting, is this barrage of letters until they constitute this Air Force Study Board. Cliff told me this story himself, and then he wrote it in his books. I'll quote Cliff for what happens next. As a reminder about, one more reminder about what the Cold War really was like. So Cliff says in this lovely book, an awkward moment occurred midway through their year-long study when the Air Force Study Board staff member asked me when I'd become a naturalized US citizen. Can you see what's coming? I replied that I was a Canadian citizen on a permanent green card, a fact that was evidently overlooked on the CV that he'd submitted when called upon. This was a problem because the Air Force Study Board rules that all studies are initially classified, even if they don't actually deal with classified materials, as was true of that particular study. After some urgent phone calls, the staffer managed to get a general to declassify his own study retroactively so that work could continue. Cliff told me other stories about when he had to be sort of escorted in and escorted out of Pentagon briefings because he couldn't hear the rest of the briefing because he was actually still, after all, a Canadian. Now he has dual citizenship, but back then he didn't. Okay. So nonetheless, that was cleared up and he could run his own study. In parallel, there was a study run by the Jasons. Again, it's a group that's probably familiar to many in the room, a group that exists to this day, also organized soon after the launch of Sputnik, of civilian scientists, mostly university-based scientists, at this time mostly theoretical physicists, who had actually had clearance. They were both citizens and had clearance to look at classified material, and would serve as sort of an informal kind of review board, almost like a peer review on behalf of the Defense Department for the US, in part to try to make sure that kind of enthusiasms from one general or another weren't departing too much from the laws of nature. So they ran a study in parallel, in fact, with one member in common. And in fact, our own Freeman Dyson, your own, in fact, my beloved Freeman Dyson, served on that particular committee, as did Murph Goldberger. There's a remarkable list who was on the Jason committee as well. So they met sometimes with the Clifford Will Air Force study, sometimes on their own. Their report was released, the Jason report was released after about 1 year of study. And about a year later, so almost 2 full years of study, the Air Force Study Board, chaired by Clifford Will, released its report as well. And so the print is so small that you can see the Jason's group included many good Princetonians. They included Freeman Dyson, Bill Press, Mal Ruderman, and Sam Treeman. So it was a local effort here as well. Okay, what did they conclude? Both reports came to the same conclusion, which is good. So both the Jasons and the Air Force Study Board agreed that in the end, the Boulder physicists had been perfectly accurate enough all along. that they weren't ignoring rotation. They were actually working with a good enough approximation for the error budget that was required. And they go through that several steps. And I find this really fascinating. This hinged on the kinds of subtleties we still work on with our students, sometimes our PhD students and postdocs and ourselves, about subtleties of coordinate systems in general relativity, now for targeting things like weapons. So here's now quoting from the Air Force, the unclassified report that Cliff Will had shared. We have independently derived equation 1 of this article that had been sent out for the independent review, the article by the Boulder physicists, and it is correct. So it was not actually the wrong equation, it was a correct equation, and as they go on to say, perfectly adequate for the uses to which it would be put. Now they go on to say the paper is not written in language similar to that of most textbooks in relativity. It is in what was called pre-relativistic language, 3 vectors, not covariant 4 vectors, let alone forms. But they say this is not surprising because most relativity textbooks are at most tangentially concerned with real-world measurements and systems. That was certainly true in the mid-1980s. Moreover, the effects that these outsider quartet have identified are not new. They'd essentially rediscovered the sanding effect, which by then was more than 50 years old. The papers are correct, but they contain nothing new. They're irrelevant, essentially. Nothing new for the purpose of time synchronization of satellite systems such as GPS. And now quoting from the Jason report, and in fact, the same paragraph appears in the later Air Force report, these discrepancies from rotation are not uncontrollable errors. They're not unknowns. In fact, they're completely computable corrections. It's a calibration effect. And the group had already done successful tests showing they could successfully measure the offset from rotation, recalibrate, send correction signals to the satellites, and move on. And they could do that while keeping everything else within this 3 nanosecond error budget. It's not an unknowable uncertainty. It's a calculable offset because the orbits of these satellites were actually known to such high precision. I love this. Clifford Will very kindly showed me his handwritten overhead transparencies. This is what PowerPoint looked like in 1984, where he had to explain in 1 hour to an Air Force general the basics of general relativity. That's a pretty good ask. So it goes through time dilation and redshift. These affect the rates of clocks. It's going to be a large offset, but a known one. And then the sanding effect is an offset, but not a change in the rate. Moreover, this has been known by international time coordination bodies for decades. They've been doing this on the ground with air travel, flight, and even with early satellites. It's a known and knowable calibration, and that's already taken into account, but it wasn't so clear because that was not actually so readily available either from the contractors or indeed from the published literature. So it took them 2 years to agree this actually has been done correctly. It's subtle, but it's okay. So this is getting toward the end here. Clifford Will's group then had to explain to the Air Force general and in its unclassified report, even to people like me, how the system actually works. What you do, and this really is what the Boulder physicists Ashby and Allen had set up from the start, you construct a convenient but, so to speak, fictitious reference frame, a convenient set of coordinates that share the origin, the spatial origin, with the center of the Earth, but that don't rotate with the Earth. And so you could define a coordinate time in that set of coordinates, that reference frame. That's what one of these fancy clocks would measure far, far from Earth, so it's not affected by any masses. And that's, of course, going to be different from any measured clock rate on any actual body moving near or on the surface of the Earth. So you distinguish between the coordinate time in this convenient but fictitious coordinate system from what's called the proper time that any actual observer would measure or record from their own real clock. You do all the calculations in this convenient but sort of fictitious non-rotating reference frame. It's co-located with the center of the Earth, and you watch the Earth rotate from that reference frame. That's what this cartoon is trying to show us here. So here's our reference clock all the way up here. Imagine that goes all the way up here. That's unaffected by any gravitational redshift. It's at the North Pole. It's not rotating and so on. And there you just sit there and watch everything else move by. Do all the calculations in that one unambiguous reference frame. And then on the last minute, you transform back to the reference frame that's going to be relevant to, say, an observer on the ground. So you transform back at the end to an Earth-fixed rotating reference frame. And then that is what's going to incorporate both time dilation and gravitational redshift and is corrected with these updates from the Sagnac effect as well. Let me conclude. So by the late 1970s, both these insiders and the outsiders agreed that GPS could only succeed if researchers took Einstein's relativity seriously. The question was never Einstein, love it or hate it. It's who's getting Einstein correct. And as they all agree, there were several distinct types of effects from relativity they had to pay very careful attention to: time dilation, gravitational redshift, and this rotation, the Sagnac effect. The question was, were they being incorporated correctly, and how would you know? And here's where this really becomes a kind of grounded, all too familiar Cold War story. Reaching consensus was really non-trivial. They were not just using different notations, we can get beyond that as smart researchers, different terminology, but really relying on different communication patterns among mathematical physicists who never thought about actually how do you talk with a satellite that's in orbit, and then these time transfer engineering experts who were very good at using light waves to coordinate clocks at a distance. All of that sort of made even more exacerbated by both formal military secrecy and sometimes informal, but still equally impenetrable, contractor like trade secrets. So how does it go from still classified technology to something that so many of us use most days? Unfortunately, it was born of tragedy. So before the network was even operational, in early September 1983, many of you might remember this, Korean Airlines Flight 007 was shot down over Soviet airspace. It was a flight that started at JFK Airport in New York, flew to Anchorage, Alaska, and the last leg was Anchorage to Seoul, South Korea. And it was on that last leg where the plane drifted quite far off course clearly into Soviet airspace and was shot down by Soviet military jets. About 2 weeks later, the US Reagan administration announced that once GPS became available, it was still 5 years out. But when this network of 24 and eventually 30 satellites was operational, that it would be made available for civilian use as well. The argument being that if the pilots had had access to this kind of technology, they would have known exactly how far, or at least much more accurately, how far off course they had flown. So indeed, starting in 1988, this was made available to the civilian market. It was still in a two-tier system, though, until spring of 2000. So between the late 80s and 2000, GPS operated in what was called selective availability, which is government speak for we select not to make it available to you. That's how administrators work. So each satellite would broadcast 2 beams at once, 2 signals, one of which highly encrypted with the sort of meter accuracy signal, and one of which was intentionally degraded but open, so that you could have about 100-meter accuracy instead of 1 meter. And that was still going to be enough for things like civilian air travel to avoid these kinds of problems, but nothing like kind of precision targeting, for example. It was only in the closing days of the Bill Clinton administration it was determined that there was no actual threat to US security if they relaxed even that. So with another software update, just sending a beam up to the 30 satellites, not changing any physical hardware, overnight, the accuracy of the GPS system went from 100 meters for all of us to 1 meter. You can see this printout from one of the federal bureaus. These are the average errors until the software update, and the errors fall by a factor of 100. They basically stopped degrading the unencrypted signal. And that's how it came to be useful for the rest of us. So with the development of these inexpensive receivers in mobile devices in most of our pockets most of the time, Einstein's crowning scientific achievement, the general theory of relativity, now helps billions of people find our place in the world every single day. Thank you.
Because David is so nice, he said he would field his own questions and I'll next the phone. David, that's David. Fine. Any questions?
Yeah, so straightforward. Oh, some questions in the back. Oh, some up front as well? Oh, good. We'll come to you next. Thank you. Yeah.
Hi, thank you so much for that. So I'm going to ask a horrible sociologist question of
That's your job.
historian,
That's
if you'll bear with me,
Yeah.
which is about some of the themes about the scientific ecosystem
Yeah.
that come out through the paper. So I'm thinking about the Cold War relationship between, an organization like JASON, university scientists,
Yes.
defense contractors, do you think the sort of debates and that were happening, like your dueling relativists, were typical or atypical of the kind of debates and relationships in that ecosystem of that time? That makes sense.
Thank you, Professor Nelson. I think through the lights I can see it's Professor Nelson. Thank you for that. It's a wonderful question. No surprise. I don't think this was the outlier. I think this was thoroughly typical, at least in my understanding, of this era of US-based Cold War science and technology. I don't say that to say good, bad, love it, or hate it. I'm saying this was typical. And I think that's frankly why the Jason Group was founded and why it even persists amid, as you well know, of course, Alondra, some searing criticism, especially at the peak of, say, protests against the Vietnam War. There's not a straightforward relationship, but one that has persisted. And I think people like Freeman Dyson, with whom I had a chance to talk about some of these things some years ago, I think many of those folks, the civilian insiders, let's say, the ones who did have clearance, who went to Santa Monica every summer for these summer studies, practically every summer, I think they were really concerned that if left to their own devices, fairly or unfairly, I think his concern was that these folks are not subject to even a sliver of the kind of peer review, which is imperfect and frustrating and bureaucratic. But has some real merits that I think we say outside the fence, routinely benefit from. And if no one's looking over the shoulder for these expensive and frankly impactful technologies, something can go very wrong very quickly. Now, I'm not endorsing that view necessarily. I think there's some wisdom to it, but I think it was also maybe abused sometimes as well. But I think it's because of that insider-outsider flow of information is quite constrained and constricted. I think there was some people who thought we better have some eyes on this. And some of the members of the Jasons will say to this day, many of you in the room probably heard them say similar things, that we killed this general's pet project 5 times, right? We're going to use neutrinos to take it. No, you're not, right? It's not going to work, right? And they would, again, it's maybe a bit of a self-serving story that I've been told, but the story was that, just over and over again, you need an extra pair of eyes or many pairs of eyes on these things. There's a very dear colleague of mine, some of you know, Ben Wilson, who's a younger historian of science, who's written a really absolutely brilliant book, it'll be out soon, showing, among other things, how much what we might call kind of pure science from some of these extraordinarily gifted people like Freeman Dyson and Stephen Weinberg and others whom many of us in the room knew and really greatly admired. Many of their questions for basic research, for example, in astrophysics, it turns out were triggered for them because they were actually doing at first classified studies of things like the interaction of high intensity radiation and materials. For example, is that warhead going to warp upon reentry? Oh, I wonder what happens with jets around black holes. That there was literally a one-to-one mapping, not always, and not for everyone, but you can trace these sort of intellectual linkages. It wasn't separate activities for them, right? Now we could ask, is that healthy for a scientific community? What if everyone had access to some of that information? I mean, that would be one of my first follow-up questions myself. The field of adaptive optics, for example, Freeman was very proud to say he helped sort of shepherd this through when it was still a classified military technology, and then later helped convince the military to declassify it for the astronomers. So would we be better off if some of these ideas had been open even earlier and accessible to a much wider community? I would like to think the answer is yes. That's not the world that we were given. That's not the world we chose to make through much of the Cold War. That's a long and rambling way of saying I don't think this story was at all atypical. I think we see that across many areas of physical sciences and probably beyond, but the physical sciences are the ones I know better.
Yeah. Question right here. Is this mic on or do I have to touch it?
It's on. Is there any theoretical limit to the accuracy of the GPS system? Is there some minimal expected error?
Good. So I'm not an expert on this, and actually others in the room might be actually on these things. I mean, if you read the internet, which I don't recommend, then supposedly the military has super duper GPS that they're not going to share with the civilians yet. Better than centimeter accuracy. I don't know if that's true or if it's in the works or if it's possible. I mean, in principle, you're limited by the kind of jitter rate of these clocks. Now, atomic clocks have gotten exponentially better than the 1960s and 70s. So if you have clocks that really can operate under hard operating conditions, like on a satellite, instead of just in a pristine national laboratory, and if they can still do femtosecond accuracy, which is, what, 1 million times better than what they were using there, then in principle, then you should be able to, if all the rest of the kind of connections can also be kept really tight, then in principle you could shrink your location accuracy accordingly. I don't know how realistic that is, and femtosecond clocks now are, they work under pristine, stable conditions, and you don't launch them in space. But in principle, as clock technologies and signal transfer gets cleaner and so on, I don't think that we're going to be stuck with meter level accuracy forever. who gets access to centimeter or millimeter or whatever the limit will be when, that's going to come back to, I think, the kinds of questions that Professor Nelson was asking us about as well. That comes down to decisions of public policy, of priorities, of access, of public good versus, kind of national security. And turns out those aren't fixed by the laws of nature, right? Those are fixed by our otherwise imperfect system of interacting with other people. Yeah.
Hi, I had a question about the to what degree of accuracy was the gravitational potential of the Earth of different points on the Earth's surface known, and how much has it improved over time? Because that's super important for the gravitational redshift.
Yes, yeah, good. So again, that actually goes maybe back even to the earlier question, or maybe in a surprising way. George Gamow was asked to comment on some of these early ideas, the great sort of co-inventor of a Big Bang model of expert in relativity himself. And he said, well, here's how you keep ourselves safe. Just don't publish maps of the gravitational potential around the United States. Don't let the Soviets know where there are mountains. I mean, essentially, right? To requisite accuracy. Meaning, if you just control the flow of information, then they'll be limited that way. He also thought that, and he had all kinds of ideas about that. So for a long time, the Navy was sponsoring efforts to map the seafloor, both for how would sound waves travel for things like submarine detection, and also in part for things like mapping to the best precision they could manage the hyperlocal gravitational potential. Which is just to say that it was a scientific question that had a particularly high priority and therefore got resources from the US military at a time when the US military was spending seemingly unlimited amounts on research that was both of great interest to geoscientists, but also of great interest and priority for operational purposes. So that's just to say that even something like, let's just map the gravitational potential of the Earth, well, by whom, to whose accuracy, who's going to put the resources forward, that becomes immediately a human, social, institutional, political question, and not just who has the best, gravimeters, although that's tied up with it. Good.
Any other questions? Yep.
Oh, thanks, Miles.
The magic wand coming.
Yeah, hi. So you mentioned that there's 4 unknowns, the 3 spatial and the time.
Yeah.
So we've got x, y in meter. What about elevation? We don't get that.
That's right. I think we can. I mean, I can't, but I think the systems in principle are doing that. And here's what other experts in the room might know better. It doesn't work well on my iPhone. I agree with that. But I think that I'm not sure what the limitation is for that. To be honest, that's a good question. Yeah, that's my own limit as merely a theoretical physicist. I don't know. The cartoon made perfect sense to me, but you're right. I'm not sure. That's a good question. Yeah.
Anyone else? If not, David, many, many thanks for
Thank you.